Okay, now as I pointed out, we could actually just use a random set of an even number of cards and show you everything here. But to be able to follow things, to make things a bit more transparent and more readily understandable, let's go ahead and use what we were doing before. And so you can choose different cards if you like. You could choose the 4 queens and the 4 kings if you wanted. There's so many different relations, categorical relations you can put on a packet of cards. And of course, there's a near infinite number of categorical relations that you can put on, sets out there of a large number of things. We're back to the very beginning, the 2-cycle structure that we had. Okay, so that puts us over here. Now, something I did with that one example of using random cards is I actually performed a Charlier shuffle. Okay, so a Charlier shuffle, many of you know this because we talked about it in class. So this is where you push off a number of cards from the top, and then from the bottom, in fact, I have a video on the Charlier shuffle, so you may want to look at that if I go through the steps for that too quickly. So you top to bottom, bottom to top, top to bottom, bottom to top. Now, despite the fact that that looks pretty messy, and it looks like it would be impossible to know where things are, and in some ways that is true, because I can do this with my eyes closed, right? And then at that point, I truly don't know exactly the order of the cards. I can't tell you what card's on top, for example. But I do know that a Charlier shuffle is equivalent to an ordinary cutting of the cards. Now, cutting of the cards is where you just take a certain number, you don't rearrange anything, take a certain number, put those down, and then the rest on top. That's a cut. Believe it or not, the Charlier shuffle is equivalent to one of those. So, in particular, what that means then, to prove it, okay, that's pretty amazing. I got back to there. We should be one cut away from the exact order we had before. Well, we are. If I just move these to the bottom, that's where we started. Okay, so a Charlier shuffle, despite its just messiness and the perception that you really are just mixing those cards. And what's interesting is even when I tell people, if I don't tell everyone, but when I tell people that a Charlier shuffle is really just cutting the card once, they will not believe me. They will not. They say, that is mixing the cards. I'm absolutely convinced that is mixing the cards. And I try to show them through example, and some of them eventually believe me, but it's such a convincing shuffle that it's actually hard to change people's opinions. Okay, so the Charlier shuffle is indeed equivalent to a single cut. Now, what that means in terms of our structures and what we talked about in class is the Charlier shuffle as a mapping is an automorphism. It is an automorphism. Why is that? Well, as we mentioned, let me just do it again, this time so that we don't get the exact same order. What does it mean to be an automorphism? Now, I know we've already talked about this in class, so I apologize for the review. But so an automorphism is a bijection from a set. Well, first off, you have to have a set with structure on it. It can be algebraic, topological, some kind of structure. And an automorphism is where that structure is preserved. The key structure or the key requirement for the structure of that entity is preserved. Okay, well, what is truly the requirement of a 2-cycle? Let's go back and review that. Well, a set of objects is a two-cycle if the following is the case. If p-equivalent cards are related by way of our categorical relation. Now, our categorical relation for today will be that the cards have the same value. Now, because of the cards we chose, it's also the case that they have opposite colors. So you could throw that in if you want. Same value, but opposite color. Here, it wouldn't make any difference. You don't have any other choice. There's only a red ace and a black ace, and so forth. Okay, so we need it to be the case that p-equivalent cards are of the same value. Okay, so remember, this is in position 1, this one's position 5. Sorry, 1 and 5 are congruent to each other mod 4. And it's because 1 divided by 4, well, that's a remainder of 1. And 5 divided by 4 gives you a remainder of 1 as well. So if you remember, these are p-equivalent, and they're also of the same value. So there you go. These are p-equivalent. Look at their positions. Divide their positions by 4, and you'll get the same remainder. These are p-equivalent, and these are p-equivalent. Okay? And I probably should start using the C-equivalent word as well. It just saves saying a lot of words. So remember, two objects are C-equivalent if they are in the same category. So the categories that we've set forth here are sets that have cards of the same value, okay? So here, going back, we could say the 3s here, they're both p-equivalent and C-equivalent. The 4s are p-equivalent and C-equivalent. The aces as well, and the 2s. Okay, now you might think the original two-cycle we had was nicer, because we had them in order, ace through 4 of clubs, then ace through 4 of hearts. Well, maybe that's the case. It appeals to our aesthetic sense of order, and all is right with the world to have it that way. But as far as the definition of a two-cycle, what we are looking at right now on the table is just as legitimate of a two-cycle as the original one, because we just need p-equivalent cards to be C-equivalent. That's all that original subset relationship, wherever it is, that's all this is saying. The cards that are p-equivalent need to be C-equivalent, okay? That's all we're doing. Okay, so this is a two-cycle, and so what we've learned or seen or been reminded of is the Charlier shuffle. You can think of a shuffle as a permutation or a mapping, is an automorphism. It leaves two cycles alone. Now, you cannot apply the Charlier shuffle just willy-nilly to these others. Create a mirrored structure and convince yourself that you can't just randomly cut that and expect the cards to be mirrored anymore. Okay, so now, as an aside, I hope to not give you too much here. As an aside, there is a Charlier shuffle that preserves all of these, and it's one that I've come up with the name because it's not out there. People don't talk about it, but boy, is it valuable in the study of cyclic and mirrored structures. I call it the Charlier 1. The Charlier 1. So what the Charlier 1 does is, let me put this one back in that original order that we started with. Sorry, if you can see that. A Charlier 1 is where you just move one card at a time. Now, it's not as sloppy and maybe as convincing as a traditional Charlier shuffle, but boy, it still looks like you would have to be a genius to keep track of where things are. Okay, so this is where you push off the top, 1 from the bottom, 1 from the top, 1 from the bottom, 1 from the top, 1 from the bottom, 1 from the top, 1 from the bottom. Now, I don't know how many people would be able to immediately conclude that what we've done is we've just done a 50% cut, but that's what it is. So a 50% cut just means we've taken the top half, which this was the top half, and we moved it to the bottom. Okay, well, why would a Charlier-1 actually be an automorphism on these other categories of structures? Maybe I shouldn't use the word category, that we're using it in lots of different ways, and the collections of structures. So why would the Charlier-1 preserve a mirrored structure? Well, it doesn't take much to convince yourself that that is the case, because if you have a mirrored structure and you cut it in half, it's still mirrored. It's not exactly mirrored in the precise way it was before, but it satisfies all of the conditions for a mirrored structure. Okay, well, it ends up that mirrored structures have a classic automorphism, and this is not one that I've discovered. It comes from something called the stay stack principle, the stay stack principle. And maybe we'll talk about that in more detail and perhaps even prove it later in the semester. It's not too difficult to prove. There's a bit of bookkeeping. There's kind of a matrix involved to keeping track of where you are when you perform a left-right shuffle or a more general RC shuffle, I call it. So here what I have for the moment is I have, this is mirrored relative to cards having the same value. Okay, so mirrored relative to cards having the same value. Great. Well, it ends up that an LR shuffle preserves mirrored structures. And what is fantastically wonderful is it doesn't matter if you stack right on left or left on right. The mirrored structure is preserved. Okay, so this will still be mirrored. Now, it won't be the exact same arrangement, right? Hopefully, people are starting to get a picture for that. The cards are being mixed, but within certain bounds that you understand, or at least we understand some of what we're doing. There's so much, I'm sure, that none of us understand when we mix things up. But I have given you the tools to understand this much, that this is mirrored, because what we need, I guess you can just call them mirrored pairs. They need to be sequivalent. Sequivalent here means that the cards have the same value. So these have the same value, those have the same value, these have the same value, and so forth. Okay? And once you have, well, maybe we can show it now down here, but you have to realize that once it's mirrored, you're one slick step away from pairing them, right? If it's mirrored and you go like this, you've paired them in value. Sorry, that went flying. You've paired them in value. Well, that's the Klondike shuffle. So if you start with a mirrored structure and then perform a Klondike shuffle, you will get an AMP. And the way that we've done it is we've gotten what's called a DMP, distinct mirrored pairs. Well, what's an AMP is where you perform the Klondike shuffle and you're stacking the cards as you go. What I've done here is the pairs are all over the place. So this is called distinct mirrored pairs. I'm sorry, we're kind of moving on. Remember the chart that I showed you. So here we go. DMP, distinct mirrored pairs are off over here. And you can do special things with those. But so anyway, I apologize if I'm throwing too much at you at once. But the fact is, once these are paired together, to get an AMP, it doesn't matter what order you stack these, which is wonderful. Okay, so many times you see card effects and people are very carefully picking up and these pairs in just the right orders. We don't care. It's an AMP. Anything I could do with an AMP, I'll be able to do with this packet. Okay, so this is an AMP. Okay, so there you go. Remember, p-equivalent cards here mean that they're adjacent, starting from the top, and non-overlapping as pairs. Okay, so first pair from the top, of course, are the aces. They're the same value. Fours, the twos, and the threes. So that is a bona fide AMP that satisfies our categorical relation. Okay, now it ends up that AMPs have a tremendous number of automorphisms on them. You can do even size cuts. An even size cut just means maybe I cut 2 to the bottom. Well, think about it. That's not going to change the fact that it's an AMP. You can do even size coats, 1, 2. That doesn't change anything. Well, it does change things. I need to be careful. It does change things. Things are changing. But the fact that this is an AMP is not changing. We're staying within the whole world, the whole universe of AMP packets, given our equivalent cards. Also an even deal. So we could do 3, 4, 5, 6. Rest on top. Oh, well, I guess that's a deal. That's kind of a coat. And I guess what we could say here is that, in fact, I'm trying to remember exactly what I had in mind there, as far as because a coat is a deal in which you put the the rest on top. But it is true that you can deal these out into even piles and then stack them in whatever order you like. And it's the same thing with a coat. Okay, let's put these back here. So maybe we'll coat 2 of them, put the rest on top. It doesn't matter if I put those on top or move them, right? Because it comes back to a even size cut. And then you can even flip an even number of cards. Okay, it's not going to change the fact that these are related, right? So you can go like that, and then I can come over here and then maybe flip these 2 as well. This will still be an AMP. Now you have to realize that this is pretty transparent only because of the categorical relation we chose. If you think back to the random collection of 8 cards that we put out, and I paired them up perfectly at the end, if we were to do this, these pairs would have no connection at all in the minds of the spectator. They have no connection. The only connection they have is the fact that you put them into categories on your secret piece of paper. Okay, so even though this is like, oh, well, there's something obvious going on there, it doesn't have to be, right, in general. Okay, so anyway, that's an AMP, and a Klondike shuffle will get you from an AMP from a mirrored to an AMP. Now, let's say we want to go back. We want to go back to a mirrored structure. Well, we can do a Monge shuffle. And what's nice here, once again, it doesn't matter which variety you use. You can do an over-under or under-over, and both work just fine. Okay, so Monge, to remind you, this is where you push off the top card. And then let's do over-under first. So then the next one goes over, under, over, under, over, under, over. That converts an AMP to a mirrored structure, guaranteed. So here we have mirrored again, right? And once again, it wouldn't matter if we had done under over. So to quickly get back to go from a mirrored to an AMP, let's do a Klondike again. This time we'll just stack them on top of each other, which is normally, that's what this means here, Klondike. You're just stacking them as you go. And to show you, of course, you get an AMP, which is what we want. And now let's do an, whoops, you can't see my finger. An under over. So now push off the top, under, over, under, over, under, over, under. Well, does that take us back to a mirrored structure? It does. It takes us back to a mirrored structure. Now, it won't be the exact arrangement of cards that we got with the over-under. And so people's perception that cards are being mixed is correct. The cards are being mixed. But once again, they're being mixed in a way that you have some or significant knowledge over how those cards are related to each other given their positions. Okay, so the structure is preserved if we're, careful, if we have structure preserving maps. Okay. Okay, so you can go from, and depending on if it's even or odd, an even or odd size packet, I don't have the result right here in front of me, but the Klondike and Monge are exact inverses of each other under the right condition. I'm trying to think if it's like the over under is the inverse when you have an odd number of cards, and the other one is the inverse if it's under over. All of that's actually listed in the book. I give you the exact inverses. Okay, great. So what we're going to look at now is we have an AM. Nope, we're back to a mirrored. Okay, well, since we're over here at a mirrored, let's go ahead and jump this way. Now there's an arrow that goes both ways. And C here is a 50% coating of the cards. Okay, so we have mirrored. So we do 1, 2, 3, 4. That's half the cards. Drop the rest on top. We will get a 2 cycle. And you're getting a feel for how the cards, they're not super mixed yet, but how, well, they will be as we continue doing this. But the cards will be changing places, but maintaining structures, depending on where you are in this diagram here. Okay, but this is a 2 cycle. P equivalent cards are C equivalent, right? As you go through them in pairs. Now we could have actually, and I've mentioned this in class, a 50% coat. Technically, this goes on top. Well, something called a super coat. It includes more than just what I'm going to show you now, but a super coat includes the case where you stack them in the opposite order, meaning you stack them in whatever order you like. So once you've counted out half the cards, you can stack them in either order, and guess what? It's still a 2 cycle. Okay. Oh, sorry. It's still a, well, here we've gone back to a mirrored. So it's still a mirrored. Okay, so let's get back to a 2 cycle. Now, to get to a 2 cycle, we have a couple of paths. We can do another 50% coat, or we can do a Monge. A Monge. Okay, so that, and it can be of either type. So we'll do over, and then under, over, under, over, under, over. Okay, so that will take our mirrored structure to a 2 cycle. Okay, so here are the P equivalent cards or C equivalent. Okay, great. And then while we're over here, you can do a Charlier shuffle, do as many of those as you like. Each one of those is equivalent to an ordinary cutting of the cards. If we want to get back to a mirrored, a 50% coat always works. So in a just immediate sense, a 50% coat is an isomorphism between two cycles and mirrored structures, given the constraints that we are looking at, like even size packets and so forth, right? So a 50% coat is an isomorphism between those structure types. But why don't we, instead of going that route, let's follow a Klondike. And in some ways, it shouldn't be a surprise that the Klondike will take us here, because it is essentially the inverse of this one. What can happen is you don't necessarily get the exact order back, but you get the reversal of the packet. Well, guess what? All of these structures are unperturbed by reversing the cards. If you flip the sequence, if you flip a two cycle, it's a two cycle. If you flip I flip meaning the top becomes the bottom, bottom becomes the top, kind of thing. If you reverse the order of a mirrored structure, it's still mirrored. If you reverse the order of an AMP, it's still an AMP. And packet reversal for everything that we will do is of no consequence. It doesn't prevent us from accomplishing what we would like to. So, okay, so anyway, where did we get? We got back to a two cycle, right? Okay, so we've done that. So how do we go from a two cycle to an AMP? Now, on my larger structure, I actually don't list the ferrule shuffle, but it's actually there. It's there in two steps. So you can get to it by way of, let's see, I think you go from here to there, and then from there to there. So if you look at what the ferrule shuffle is doing, it's kind of consists of two steps. You're cutting the cards in half, and then you're interlacing them. So the ferrule shuffle is not listed as going down, but it's actually there. It's just the composition of two mappings. So, okay. So here I just view it as an honest goodness standalone mapping. So the whole set of actions is going to be viewed as just one process. Okay. So once again, two cycle. So a ferrule shuffle. How does a ferrule shuffle work? Well, that's where you have the card. You split the cards in half. So you split them in half. 1, 2, 3, 4. You split them in half. And then there is what's called a ferrule in and a ferrule out. Either one works. Hooray! We don't have to worry about in or out. So what's a ferrule in? Well, so if you remember, let's see, what did I do? This was the top. This was the bottom. Okay. So a ferrule in, that's the first one listed. Okay, what you do here is, for it to be an in, this top card, this one right here, needs to eventually go under the top card there. That's why you say it goes into that packet. Well, the way that you do it is you have to begin with this one going lower than that one. So you go like this, and all you're doing is you're just interlacing those perfectly. That's a perfect ferrule shuffle, is what it's called. And in fact, it's a perfect ferrule in shuffle. And it will always take a two cycle back to an AMP. Always, always. And if we had done a ferrule out, it would have worked equally well. Okay, so maybe we'll show you just one more thing, because this video is getting quite long. We haven't gone from an AMP to a two cycle yet. And the way to do that is by way of an LR shuffle. And there are other ones, not very many. There's another one as well that we probably should show you, but it's on our larger map, a diagram. So the LR. So this is an AMP. An LR is where you go left, right, left, right, left, right, left, right. We can do random stacking of the cards. That will take us to a two cycle. Always, 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 always. Two cycle. So if you notice, we have 2 here, 4, 3, and then 1. Okay, so we have a 2 cycle again. Okay, now as I mentioned, you can stack left on right or right on left. In the diagram, I'm sorry, I claimed that we were going to do the simplified version, and I keep bringing in these more advanced things. But on the diagram, it says R, LR, R, LR. Well, what's the R for? It means random. A random left-right. Well, it's random up to a point. So random LR means that, okay, well, let's see. We need to get back to an AMP. So let's do that. Oh, by the way, here's another way to get back to an AMP is just deal out the cards into half the number of cards you have, and then go ahead and stack them. Actually, you can stack these in any order because you've already paired them. Okay, great. So, okay, so here we're back to an AMP. And so what I wanted to show you was an RLR. And now what that means is, so as we deal out left, right, so I have left, right. Ordinarily, this next one would go left, right? Correct? But what you can do, as long as you build up the structure, you build up your levels, you build up both levels before you move on to the next one. Okay, so I don't know if you noticed what I did. Well, I'll do it here. So ordinarily this would go here left, but you could actually go over here. But we have 3 here and only 2 there, so we need to finish that level. And then you can come over here or there, it doesn't matter, and then stack those. And the amazing thing is, it's a 2 cycle. How is that possible? How is that possible? Well, it is. So it's now a 2 cycle. And it's starting to look a little messy. If you look at how the colors and the values are starting to kind of mix up. The other one I wanted to show you is, it's called an upjog. It's an automorphism on mirrored structures, and that's on the diagram. But it also converts AMP packets to 2 cycles. So an upjog is where you push the top card over, and then maybe you can do evens or odds. So here I'm doing the even. An even position card gets moved forward. The next even position card, which is the 4th card, gets moved forward. The 6th card gets moved forward, and then the 8th. And then you strip these out and randomly stack them. Aren't we glad for that? So that will go from an AMP to a 2 cycle. So here we have aces, 3, 4, 2. That's a 2 cycle. Okay, and you can do an even upjog, which is what we just did, or an odd upjog. That's where you push the odd position cards forward. Okay, I think that's enough for one day. I'm pretty tired, so we'll see you in class. And if you can practice these and master these and get a sense for why they work and how they work, we can look at the proofs that confirm that they in fact do convert these structures, either preserve a structure, so where we're looking at an automorphism, or an isomorphism where they're converting structures from one kind to another. Okay, well, thanks for watching.